So we stopped in the last lecture by looking at the gradients in the boundary layer. So we introduced the boundary layer approximation, where we said that the x component velocity is much larger than the y component velocity, and we said that du by dy is actually larger than du by dx, and dv by dy is larger than dv by dx. Note that I made a typo. This should be x and not, this should be y and not x. Okay. So anyway, so the way to introduce the boundary layer approximation, I suppose that it has been taught in your fluid mechanics course. So you have to do what's called the order of magnitude analysis. Okay. Yeah, so let us assume for now you will actually see it, because if the forced convection, if the flow rate is significantly larger, then body forces don't play much role here. So we will actually see that. Okay. So particularly body forces play an important role when you have natural convection, not in these kinds of force systems. Alright, so supposing if we say that the free stream velocity is u, okay, so that's the velocity of the fluid outside the boundary layer. So that's the velocity of the fluid outside the boundary layer, okay. And suppose we say that the v is some representative velocity in the y component direction, okay. So that's the u is the reference velocity, free stream reference velocity in the for the x component velocity. So this is the reference velocity for u, that's the velocity in the x direction. And if this is the reference velocity for v, we still don't know what this capital V is. We know what u is the free stream velocity, okay, and L, let's say it's the length of the plate, so that's the reference length scale in x direction. So I define coordinates as x and y, okay. So remember we talked about length scale in conduction. Similarly, L is the length scale in for this problem, okay. And delta, which is the boundary layer thickness, because we said that the velocity of the y component velocity is 0 at y equal to 0, and it's also 0 in the free stream location, right. So which means that the fluid is moving in the y direction and it is bounded between y equal to 0 and y equal to delta, right. So the fluid stream outside the boundary layer is primarily going to move in the x direction. Outside the boundary layer? No, no. No, not really. So if you look at far away in the free stream, it will be primarily in the outside the boundary layer, right? But that's because your boundary layer is defined as 99% of the energy. So supposing if you take 100%, then you will have 0 y component velocity, because it has to be free stream. It has to be, because whatever fluid that is actually moving in the y direction here, that is actually compensated by the retardation of the x component velocity. That's what actually brings the continuity. So if you actually do the continuity balance, you will see that the y component velocity has to be 0 in the free stream. Otherwise the fluid is not going to move, the primary direction of the fluid is not going to be in the x direction. When you say large, what do you mean large? No, what is it in y direction? Yeah, is it going to be within boundary layer or outside boundary layer? It's if it is outside boundary layer. No, you will not. No, you will not, because if you actually write a continuity equation, okay, supposing you say you write continuity equation, just wait. So if you write a continuity, if you say this is your control volume, okay, you write your continuity equation here, okay. Now here you are definitely going to see fluid which is actually moving out of the control volume, right? Because now this is inside the boundary layer and the fluid stream is still experiencing the friction which is offered by the interface. But supposing if you write a control volume here, you will have a mass flux not here, you will have a mass flux here. No, you will not. So you write it carefully, you will not. You will not have a mass flux. Well outside the boundary layer? No, it will not be. It will not be. You will not have well outside the boundary layer, you will not have mass flux. Then which means that the fluid is no more moving in the x direction. You're going to have a net pressure gradient in the y direction. In fact, you're going to see from order of magnitude analysis that the net pressure gradient in the y direction has to be 0. We'll see that in a short while. Okay. So anyway, so if delta is the reference, that's the reference length scale in y direction, that's the reference length scale in the y direction, okay. So now if you look at the y component momentum balance, we'll come to the x component in a short while. If you look at the y component momentum balance, you will have u dv by dx plus v dv by dy, that should be equal to minus 1 by rho dp by dy plus mu by rho into del square v. Okay. So that's the y component momentum balance. Now the order of magnitude of u is the free stream reference velocity. So u dv by dx would actually scale as u, that's the order of magnitude for the x component velocity, multiplied by v, which is the order of magnitude for the y component velocity, divided by L. Okay. So note that we still don't know what v is. So how do we find v? We use continuity equation. So from continuity equation you will have du by dx plus dv by dy, that's equal to 0. Okay. So from here you will see that u by L, which is the order of magnitude for u, and L is the order of magnitude for x, plus v by delta, that should be equal to 0, right. So from here we find that v should actually scale as u into delta by L. Okay. So the order of magnitude of the y component velocity is scaled as the free stream velocity multiplied by the boundary layer thickness. Okay. Alright, so now with this, so which means u into dv by dx would actually scale as u square delta by L square. Okay. Now if we look at v dv by dy, okay, v scales as capital V and dv by dy scales as v by delta. Okay. So that will be v square by delta, and that will be u square delta square divided by delta into L square. So that will be u delta by, oh I missed an L, u delta by L square. Okay. So which means that, oops, u square delta by L square. Okay. So which means that u dv by dx and v dv by dy are actually of same order of magnitude. You can clearly see from here, this is u square delta by L square, and exactly that's the same scaling you get for v into dv by dx. So that's an important observation, that so v into dv by dy. So the first two terms in the y component momentum balance they actually scale to the same order of magnitude. Okay. So let us look at the pressure term now. So dP by dy, okay. So suppose if delta P is the pressure gradient in the y direction, so delta Py, so this will scale as rho into delta, okay. So y direction scales as the boundary layer thickness. Now delta Py, okay, so that's the, so delta Py is given by the inertial, what are the pressure terms in terms of velocity? How do we write pressure delta P in terms of velocity? The knowledge equation. So we get, so that scales as rho v square by L, right, into 1 by rho into delta, okay. So that will be v square by L into delta, but we know that v scales as u into delta by L, right. So that will be u square delta square by L square into delta into L. Oops, I put an extra L. Yeah, it's wrong. So this should be rho v square by delta P scales as rho v square by 2, correct, right. So that scales as rho v square by 2, okay. So if I take modulo constant, so this really scales as u square delta by L square, okay. So that's the scaling for delta P by rho into delta. So therefore delta Py, that scales as rho u square delta square by L square, okay. So now, so that is rho u square into delta by L the whole square, okay. So in boundary layer approximation, we said that delta is much smaller than L, right. So therefore, because delta is much smaller than L, so delta square by L square will be significantly smaller than 1. So therefore you approximate, therefore you expect that the delta Py, the pressure change in the y direction should actually remain approximately constant, okay. So which means that dP by dy should be approximately 0, okay. So if you expect that the pressure gradient in the y direction approximately remains constant, the pressure change remains constant, then you expect that the pressure gradient is 0, which means that there is no net flow. Remember that it is only a net flow. This does not mean that the y component velocity is 0. It only means that there is no net flow of the fluid in the y direction. All the primary direction of flow is in the x direction, okay. Alright, so similarly, we can do an order of magnitude analysis for the x component velocity momentum balance. It's very similar. So you do exactly the same analysis. So you will find that the x component momentum balance will essentially reduce to u du by dx plus v du by dy, that is equal to minus 1 by rho dp by dx plus mu into mu by rho d square u by dy square, okay. So you have to do exactly the same. The tough part is the y momentum balance. The x momentum balance is very easy to see why the second gradient should not be present here. You simply introduce the scaling variables, you will see that that order of magnitude is much smaller than all the other terms, so you ignore it, okay. And similarly we can do for energy balance. Again the idea is same, dt by dx equal to K into d square T by dy square, and mass balance will be U dCA by dx plus V dCA by dy, that is equal to dAB into d square Ca by dy square. Okay. So, that is the mass balance. Okay. So, this is after you introduce the boundary layer approximation that the gradients in the y direction are significantly larger than the gradients in the x direction. So, once you introduce those approximation, this is the reduced equation that you will get for the dynamics of the velocity, temperature and the concentration in the boundary layer. Okay. Of course, dP by dy is 0. So, that is your y component momentum balance. Rest of the terms they are not. So, you see there is an extra delta, they are not same order, right. So, delta P by rho, right. So, you have to divide by density, right. So, correct. So, if you actually, so note that so you have to factor the delta into account. So, if all of them are equal order of magnitude, okay, and because delta P, because delta Py scales as rho into u square delta square by L square, you expect that that should be constant, and that is because the scaling is dP by dy, okay, because you have a 1 by delta, right. So, that is why. So, all of them are of same order of magnitude, okay. Now, you can't cancel out any terms. So, all you can say from that is only that the pressure is approximately constant, that is all you can say. No, if you assume that the delta Py which comes out from the scaling that it is approximately constant, then it would reduce into the factor that dP by dy is 0, right, because all the other terms, although they are comparable, but they are very small, and therefore dP by dy has to be 0. So, if the order of magnitude analysis tells you that the pressure change is constant in y direction, then you would naturally expect that dP by dy is approximately 0. Again, it is approximate, okay. But y scaling is very small, right. So, if the pressure change is very small in that direction, then the net pressure gradient has to be approximately 0. Otherwise you are going to have a net flow in y direction. So, there is no net flow in y direction, the net flow is only in the x direction. There is a y component velocity in the boundary layer because the fluid sees it experiences a friction with the wall, it experiences a friction at the interface, but the net pressure gradient in y direction should be 0, I mean approximate, very important, it is only approximately 0, okay. Alright, so now I am going to introduce some scaling. Okay. So, suppose I say that x star is my new variable, okay, and I scale it with the length of the plate, and y star also I scale it with the length of the plate because that is the measurable property. So, the boundary layer thickness is not a measurable property, it is not something that you can measure, okay, and then I scale u star, u as the x component velocity divided by the free stream velocity, it is capital U, okay. So, if capital U is the free stream velocity, and if I say V star is V by capital V, capital U, okay. So, I use the same velocity, free stream velocity, in order to scale the x and the y component because that is the only measurable quantity that I have, okay. So, similarly I could scale Ca star, the concentration of the species, with the free stream concentration, and the temperature with the corresponding free stream fluid temperature, okay. So, if I introduce these scaling, so now I am going to non-dimensionalize these equations. So, that will be u into u star, u into du star by L into dx star plus u into v star, u into du star by dy star, okay. That is equal to minus 1 by rho. Now, pressure you can actually scale with rho v square. So, if I introduce P star as P by rho v square, okay. So, if that is the scaling that I introduce for pressure, so that will be rho v square into dP star rho u square, thank you, okay, divided by L into dx star, okay. So, that is the scaling for pressure plus mu by rho into u into d square u star divided by L square into dy star square, okay. So, now if I cancel out all the like terms, and so this will become u star into du star by dx star plus v star into du star by dy star, that is equal to, so now I bring L by u square, so L by u square goes out, rho will cancel out, so it will be minus dP star by dx star plus, now I have L by u square, so that will be mu by rho into u by L square into L by u square into d square u star by dy star square. What is this term? This is 1 by Reynolds number, okay. So, that will be u star du star by dx star plus v star du star by dy star, that is equal to minus dP star by dx star plus 1 by Reynolds number defined based on the length of the plate, okay, into d square u star by dy star. So, Reynolds number is nothing but rho into u into L by mu. So, if I know the kinematic viscosity, which is mu by rho, so Reynolds number is u into L by mu. So, this is the Reynolds number for the flat plate, okay. This is defined based on the length of the flat plate. So, this Reynolds number will tell you what is the transition from laminar to turbulent flow. So, this is the ratio of, Reynolds number is ratio of inertial over viscous forces. The ratio of inertial over the viscous forces, okay. What is the inertial force? Half rho u square, that is it, that is pressure divided by L, multiplied by L square, that is the stress, okay, multiplied by, okay. And what about the viscous forces? Mu u, okay, u over L multiplied by L square, okay. So, that is what gives you the ratio of inertial to the viscous forces. So, once you have this, so it tells you what is the effect of inertial and viscous forces on the fluid flow. That is what a Reynolds number characterizes. So, if you know Reynolds number, then the properties of the fluid will tell you what is the nature of the flow. Okay. So, it captures, it incorporates all the properties of the fluid like density and viscosity which affects the fluid flow, and it characterizes as to what should be the nature of the flow.